Great. Welcome, everybody, to our next in the series of In Discussion With. Today, we're privileged to be with Giles Boon of Gale Snowden, who's going to be presenting the UK's first Passivhaus leisure centre and pool to us, which is in Exeter, St Sidwell's Point. It's a really interesting talk, and I'm sure everyone's really looking forward to hear about the development of this project. So that will start momentarily. And as usual, if I just quickly run through the other events that are coming up, we've got 4 events scheduled moving forward. We've got one coming from Cantifix, which is about solstice glass, which has been developed by Oxford University. After that, we've got Honeywell in conjunction with TH White on the 15th of September. We've got SIDWELL'S doing a planning update on the 29th of September, and then we've got a talk from Autodesk Generative Design and AI, and that's on the 13th of October. So we've got some really interesting talks from various different areas. Those are all CPDs in 43 events. So as usual, once we hand over to Giles, if you've got any questions during the talk, please do add them into the chat box, which we'll field towards the end of the talk. This is obviously an in discussion with talk, so it's slightly longer. So we're scheduled to finish this at 2 o'clock as opposed to 1:45. And if you have any issues, again, just please pop anything into the chat box and we'll try and field that between us. So that's all I have from SIAT Wessex. I'm going to hand it straight over to Giles. Thank you again, Giles. And we're going to be here in the background if anyone needs us.
Thanks, Usman. And thanks everyone for being here today. Thanks for the introduction. I think it's a privilege to be able to show you some of the work that we've been doing in Exeter. We've titled this In Discussion With the UK's first Passivhaus leisure centre, but it might be worth noting that it's actually the world's first, so multi-zoned Passivhaus leisure centre or swimming pool. We have to be slightly cautious about how we term these things and what we purport to have done, but yeah, definitely a world first in terms of multi-zoning and Passivhaus accreditation. So now there's only so much we can go into over the next 40 minutes or so, but from the perspective of a technologist, we'll be looking at a few different aspects to this project. First, we'll cover some Passivhaus principles, because no doubt there are some of us in the room who aren't up to speed with some of the aspects of Passivhaus. No doubt there are. We'll be looking at some guidance from the Passivhaus Institute on swimming pools. We'll be introducing the St Sidwell's Point project proper. We'll be presenting a sample of different technologies and approaches to the project, and also looking at some lessons that we've learned along the way. Not wishing to dwell on my CV, but I am a Principal Chartered Technologist at Gale Snowden Architects. I'm also a Passivhaus designer. I'm also a lecturer at UWE, so I teach degree students, and that is on an accredited programme, for which I'm programme leader with my colleague David Noble on the programme, an accredited programme by SIAT in architectural technology and design. I try to incorporate Passivhaus principles into the learning materials and assessment wherever possible, and also in industry, my time is generally, or the majority of it, is booked out for consultancy to advise on building envelope design for low energy and passive spec building envelopes. A little bit on Gale Snowden Architects. So I've been working with Gale Snowden Architects for 8 years now. We're involved in all these different aspects of architecture and engineering in construction, and we also do a lot of collaboration nowadays with other practices more and more. So if you're part of a practice and you'd like to work with us, we'd be happy to hear from you. Just get in touch. Okay, so we're going to rattle down through these. These are 6 really key aspects or characteristics of a passive house building. You have to get each of these right, and we're going to take them. We're just going to kind of briefly skim over what each of these means. So, compact building geometry. That means the ratio between the surface area of your building and the floor area, or the treated floor area specifically. And that means that when you take that ratio for a smaller building, typically you have a less compact building geometry, and it's about trying to reduce surface area so that you're reducing that heat loss. High levels of insulation. Obviously, we beef up the insulation, we reduce those U values, and that reduces the transmission of heat. Very high levels of airtightness. I mean, that is a classic passive house requirement. So there's our insulation. Actually, this photo is taken at St. Sidwell's Point, and you'll see 250 mil of insulation stuffed into a cavity. It's not an external wall it's actually an internal wall that's insulated. It's part of the envelope, but that gives you an idea of just how much mineral wool insulation we need to achieve those U values. To give you an idea of what 0.6 means in terms of airtightness, when we're looking at residential buildings, you might look at the area of 20 pence pieces. So that would be your typical air leakage in a house. With passive house, the equivalent area across the whole of the building would be a 5 pence piece. And that's all those little pinpricks, dots, tears, rips in your air tightness layer, which needs to be continuous around your building. MVHR systems, if you don't know already, they are the best technology in the world. In my view, they're just great. You take in some warm, you take in some cool fresh air, you pass it over a heat exchanger, and you transfer the heat from the warm air that you're taking out from the wet spaces, and you put it into the fresh incoming air to the tune of 90% efficiency. So by getting that temperature gradient across the heat exchanger, you can transfer nearly all of the heat energy to your fresh air that's being supplied to bedrooms and bathrooms, to bedrooms and living spaces. South-facing glazing is critical in a passive house, and that's because within certain parameters for overheating, we are trying to get as much solar energy into the building as possible, and that also means reducing the amount of glazing in the northern hemisphere to the north. So in the southern hemisphere, obviously it would be reversed, but large areas of south-facing glazing. And comfortable internal surface temperatures, and this is one of the thermal comfort criteria for the standard. It's also part of ensuring decent build quality, but what the Passive House Institute do is they split up the globe into a set of into their own climate zones, and they say in this zone you need a minimum internal surface temperature throughout your envelope. And in this zone, you need a different one. In the southwest, in the UK, it's about 14 degrees, and that varies from zone to zone. And it's all about balance. So we have our energy losses, our energy gains, and in terms of the heating energy of your building, we need to recognize that we've got losses in terms of transmission through the windows and the walls. We've also got losses through ventilation, not just through the ventilation system, but also through infiltration when the wind blows. And then we're trying to balance those out with the solar gains that we get through the windows, provided we're not overheating the building. Internal gains from the kettles, from other appliances, and then the active heating in red. That's what our heating system is doing to make up the difference. Okay, so what is it about swimming pools that's so energy hungry? Why do swimming pools use so much more energy than other building typologies? Well, let's take a look at these two graphics. So these are taken from a BRE document that was published in 2001, and it sets out it actually sets out different types of leisure facilities, and it breaks down the different spaces within each facility. So the floor areas on the left, and on the right, it actually gives us a breakdown of those different categories of space, and then an indication of the amount of heating energy it requires for good practice. So that's GP in that right-hand column, and in the rightmost column, a typical leisure centre at the time, or a typical space. And you can see, I mean, look down that list. I mean, with the exception of wet changing and showers, because obviously when you're running hot showers all the time, you're having to heat that shower water. Bowls Hall, 130 kilowatt hours per meter squared. We're talking about per meter squared of floor area here. So we're not talking about just because the space is big, it's actually per meter squared, it's a rate. So that 1 meter squared of floor area is using that much energy to service in a year. And the difference is an order of magnitude. So why? Why is that? Well, one reason might be because we have higher temperatures in pool halls. So you look at so we've got two graphs here. On the x-axis, we have time throughout the year, and on the y-axis, we have temperature. And what the Passivhaus Institute have done here, this is actually taken from some guidance of theirs on swimming pools, is they've shaded the area above the outside temperature up to the temperature that we want to bring that space up to. So in a residential building for Passivhaus, that's 20 degrees. And on the right, we have a pool hall. That's 32 degrees. And the area the area that's shaded is obviously a lot greater, but you can notice that even in the summer, we have quite high heat loads just to achieve that temperature. And of course, that's to make it comfortable for us to walk around in our swimwear. But in the winter, look at the heat load that you would have to achieve in February just to get, or February in a typical year, just to get that temperature up from, I don't know, -5, -10, whatever temperature it is in Exeter or Bristol or Wessex. So that might be one reason why, because we have to actually heat the space a lot more. Look at the chart on the right. Notice that along the top we have space heat, pool water, direct hot water, and notice that the pool water energy is the same amount of energy taken as the energy needed to heat the actual space itself. And that might give you a clue. And we look down the left, we've got high rates of thermal transmission, because like we've just said on the previous slide, lighting and domestic hot water, of course, the hot water for showers, high rates of ventilation because they're more humid spaces, heating and cooling adjacent spaces. So in a leisure centre, especially if you're cooling a gym and it's next door to a pool hall, that might not be ideal. Pumping of the pool water, heating of the pool water. But when you have evaporation off a pool, you get latent heat loss due to evaporation. That's the energy it takes to change state from a liquid to a gas. And that is a massive factor in that orange box, that that pool water heating. So how do we deal with that? Well, think about it. We've got a passive house envelope. So we put a nice big woolly airtight blanket over your pool hall. That's better insulation, better airtightness, triple glazed windows, careful attention to detail with the thermal bridges. And that means that you have a reduced risk of condensation. So like we were saying before, we model all the thermal bridges, we make sure those internal surface temperatures are as high as possible all the way around the envelope, and that reduces the risk of internal surface condensation. That means that we can allow the humidity in the pool hall to rise. That in turn creates less evaporation off the pool surface. So not only do we have reduced space heating demand, we can reduce the pool water heating demand as well. Not to mention we have loads of insulation under the swimming pool. And there are other benefits as well. So no recirculation of air, and that reduces the loads on the air handling units. And how does that translate to through to our passive house requirements for our envelope? Well, this table again, it's from this guidance document to passive house swimming pools. You can find it online quite easily. It's open source, so you can download it. But you can see here, so if we look on the left, indoor temperature in the table, relative humidity 50%, typical house, FRSIs in at certain temperatures. This data is just taken off a psychrometric chart, so 0.58, and then as you increase the indoor temperature and as you increase the relative humidity, you actually increase the risk of surface condensation. So you need to create those limits on how low you can have that surface temperature. So FRSI as a figure is a ratio. It's a ratio of the temperature of the internal surface to the temperature of the indoor air. With pool halls, the Passivhaus Institute actually, they model these in the PHBP and then they specify specific requirements. So for St. Sidwell's Point, we have an FRSI at a surface resistance of 0.25 meters squared Kelvin per watt to be 0.7. And in the pool halls, that's risen to 0.8. Bit of history. Well, St. Sidwell's Point isn't the first one in the world in terms of swimming pools. 2 test projects were done in Germany. One was in Bamberg, another one was in Lunen. And these paved the way for a load of research to be done by the Passivhaus Institute. And out of that came the Passivhaus Institute's input into St. Sidwell's Point and the guidance document that I've been mentioning. So St. Sidwell's Point is its project value has been targeted at 36 million. To be honest, that's crept up from lower than that at pre-tender, and of course, you know, these things do inflate. So, but the team is a client of Exeter City Council. We've done quite a lot of work in the past with Exeter, and Kia are our contractors. And I mean, I'm not wanting to blow wind or anything, but both teams are they're epic, they're brilliant. And so far, I mean, we're a few months off completion, but so far they've just been really good to work with. The project's part of a master plan in the centre of Exeter. So if you notice, or if you know Exeter, then you'll notice that we've got Paris Street here, and then we've got St. Sidwell's Point over on the right, and it's the first part of redeveloping this block, which actually runs along the side of Sidwell Street in Exeter. Now, Passivhaus isn't the only environmental factor, and of course with standards like BREEAM, we have lots of different criteria and points, but Exeter City Council wanted a facility that was not just a benefit to the local community, but that would be a destination for people all around the country to come and experience for themselves whilst they're away or on holiday, so they can travel down and actually experience a building that's not just very comfortable to be in, but that's also healthy. And we're taking principles from the Institute of Biobiology and Ecology, but also a building that's going to really stand up against future climates of increased temperatures and increased wind-driven rain. So where do you start when you design a passive house envelope for a leisure centre? Well, we obviously have the Passivhaus Institute, they're not just certifying the project, they're setting all the criteria. They're calling the shots in terms of target FRSIs and U values and so on, psi values. So, well, we literally strategize the airtightness of the whole building, and we recognize where the thermal bridges are in the whole building at the outset. So we're talking about early stage 4, maybe even late stage 3, kind of just working out exactly what our airtightness layers are in every assembly, putting them into a section, labeling them, focusing on the junctions, looking at how we can create continuity, and that in itself is an exercise. In terms of thermal bridging, there are areas that we cannot influence the design. So under the building, not in this section, but there are places in the building, say, where we have drainage in certain places and substructure walls coming through from outside through our envelope into abutting the back of retaining walls. And those thermal bridges need managing in different ways than just isolating them with thermal breaks. This is a list of U values. So these are taken from pre-tender, and this is actually set out by the Passivhaus Institute from their PHBP. And you can see U values 0.14, 0.13, 0.09. We always tend to put a bit more in the roof anyway. But then you have this right-hand column without brackets. The facade brackets have such a significant influence over the envelope, we are factoring them in from the outset. Some pre-tender design assemblies. So here we've got 2 examples of wall assembly, and these had stage 1 contractor input. We're not talking about RIBA stage 1, we're talking about 2-stage design and build, so 2-stage tender process. And in these assemblies, we're recognizing where we have fixings from facade brackets, where the air tightness layer is. So at this stage, we were looking at its titled plaster finish air tightness line on the lower example. So that was our air tightness. We used that from our experience because it's a really robust airtight layer. You can see it in the finished building, you can touch it, you can see cracks. If someone drills through it, you can actually see where the air tightness perforations are. And then areas where we couldn't have block work, we had metal stud and used the cement particle board as the air tightness layer. Implications of that are that it gets covered up at certain stages, so you need to make sure it's airtight before you cover it up. Okay, so I think the key point in designing an envelope like this is you can't really do it justice until you can optimize through a process of drafting or designing, assessing that design, analyzing it, and then iterating that design. So you're just repeating over and over again. And that's what we did pre-tender. We went through and through all the key junctions, looking at how they were put together with some subcontractor input, just trying to understand, you know, what the transmission losses were and how we could do things like positioning the glazing in relation to the insulation and you know, designing the support for the eaves in a different way. Inevitably, when the contractor comes on board proper and we start site, there are changes that occur, and there were many changes that have happened since Kia come on board. One of them was, well, this isn't a definitive list, but for example, one of the first things that happened was CalZip stopped producing the specified product for the standing seam. So Euroform was put forward, and of course we had to assess that against the environmental factors or the Passivhaus requirements. There was a change to 12mm cement particle board from 24, and that was because of health and safety and cutting on site and the weight of the boards. And there was a massive push to change the majority of the wall areas which were rendered blockwork to metal stud work. Why? Well, when it's coming down to program and the contractor needs to speed up, then understandably you have to work on some level, despite the risks, to find a way of you know, of changing the design. And so we increased the areas of metal stud work, and that's helped them to work in the way that they were more used to working. One of the things Kia did that I really liked actually was to produce this mock-up in a room on site, an old room out the back of the bus station, and that allows them to test the design in a couple of ways. Not to validate the design, but to look at buildability, to pressurize it in certain ways and look at air leakages, to educate their team, to try and work out where they could, if they wanted to, make their own improvements on the design in order to reduce their risk. So these photos were taken back in 2019, actually. So coming on 2 years ago. And if you've never seen insulated substructure, this might be what it looks like. You know, we're talking about 250 mil of XPS on pile caps and on columns below ground, where there's just no opportunity for thermal breaks, and you need to reduce that thermal transmission. And of course, sometimes piles don't go exactly where you expected them to, so we have to measure the thickness of the insulation that's left and test that in thermal bridging software. This was taken a few days after the glue lambs went in. And again, the following month, once the CLT had gone on the roof. And here recognize that the CLT beams aren't lining through with the edge of, or the outside face of the concrete. That again, unexpected, subcontractor's design, subcontractor not changing design. You know, then we and the design team, the integrated design team, step in. We explore a method of making that airtight, something to support an airtightness layer, and how we can keep that continuity with the other elements. Monitoring on site, especially with rainwater downpipes. Notice on the image on the right. So this was taken few months ago. Sometimes things just don't go in as you expected them to. You know what I mean? And when you look at that rainwater pipe, you might think, okay, well, there's a bit of insulation tucked behind it. But as it tends towards the backing wall up towards the top, that had to come out and go back in, because as you can see from our thermal bridging calc on the right, we've got quite a lot of transmission through. So what you can actually see here is the little bars. I don't know if you can see the mounted fixing there, the little clip. We've got thermal transmission through those. We've modelled them. This one actually has 3 downpipes. It's on the other side of the building, and yeah, you know, if you model something and assess it, and then you specify something as a minimum requirement, then that's how it needs to go together. This so this was a remodel during construction. This is where we had a few unexpected changes for the curtain walling screen that you can see from the roundabout if you drive around that way. So the curtain wall was originally further inbound, and one of the things we always try to do with Passivhaus windows is to get that glazing as close to the center of the insulation as possible, because it reduces that thermal bridge as well as over insulating the frames. At an early point during the construction, the backing boxes increased in depth because the supplier, the subcontractor, had recognized that their back boxes modeled pre-tender were actually too small for the wind loads imposed on that screen, and so they increased the next size up. That added 50 millimeters, and then the subcontractor themselves wanted to pull the curtain wall screen off the building so that they had space to get their hands through and fix it in certain ways. And that pushed the glass right out beyond our insulation zone. And so remodeling, looking at how we can fix cladding in certain ways, and trying to reduce the impact across the envelope was part of that process. Some photos of curtain wall installs. So we've got install with different fixing methods. So on the right we've got the spigot plate bracket, where we're taking the EPDM as the air tightness through into the reveal to link it through with other airtight elements. In this case, we're actually taking everything through so that it can be inspected from the inside across all the curtain walls. Here on the left, it's a different fixing method. So in this case, we're bringing the air tightness up from the roof below, and we're not taking it through to the inside, we're just taking it straight up to the seal at the sill. And then at the top, something that we as designers don't tend to think of is the impact of temporary works. And so those temporary works needed taking off before they could complete the air tightness, bringing that down to the seal. The spigot plate fixing methods, the one on the right, obviously, so the one on the left, we can see that EPDM coming up through. It's just been left hanging for now and taped to the sill, to the concrete. On the right, that EPDM isn't in place, but that would just be dressed up and over. Okay, so what lessons have we learned? Well, I think the biggest lesson of all is it actually comes down to airtightness testing. And when you design a building like this, the design of the actual building has been done by another company, another member in the integrated design team, Space and Place. But when you start to create a building like this, you need to have an appreciation for how it's actually going to be tested, how it can be split down for sectional testing, for example, how you can isolate certain areas to test them, partial testing, interim testing, and big contractors, they tend not to want to close down a site to test. Obviously with a house, you just have a testing day, but with a big building like this, your work is progressing through the building all the time, and to turf everybody out for a week whilst you test and find all the leaks is not something that that the big contractors program for, and that's something that we as a design team hadn't appreciated, but it's also something that that the contractor I don't think had appreciated at the time they tendered. The value of the two-stage design and build process, well, yeah, maybe a lot was actually lost in the transition from one contractor to the next. And insulation fixings, watch out for those, because when you're fixing insulation with the standard fixings, if you are drilling a hole through a substrate that is your airtightness layer, you need to make sure that it is sealed at the point of penetration. And when you have insulation on the wall, you can't access it. And if you have metal stud with the lining on the inside of that, obviously you can't access it there either. So we had some exploration of different fixings for insulation and the impact that would have on the U value of the wall. The risks, well, air tightness failure. That's managed through meticulous attention to detail, both on site and during the design. Overheating, that is that's managed through modeling, through the PHPP, and also some dynamic modeling that was done at stage 3 and stage 4. And also mold growth. Obviously we don't want those internal surface temperatures to drop down below a certain level. So we're continually modeling and testing when details change. What about achieving net zero carbon? Well, we've been working with a few other projects, so a lot of the work we do now is consultancy, but net zero carbon is a thing now, and we it's not something that I personally got involved in a lot in the past, but the benefit of the Passivhaus approach to building fabric design in achieving net zero carbon as a methodology, despite whether or not you're going for a certification or not through Passivhaus, it's a real benefit. So that concludes the didactic part of the session. Are there any questions?
That's great. Thank you for that, Giles. That was extremely insightful and great to finish with a visual. You mentioned it's 2 months off completion. Is that roughly sort of? So we're going to see it sort of autumn, winter this year?
I think so, yeah. We are, so looking at the building, we're looking at 2 to 3 months from completion. So what are we now? August, September, October. Yeah, a couple of months.
Okay.
They've, to be honest, they've got a lot to do, Usman. There's a lot that needs to go into that building before they open it to the public. But the date that we're given at the moment is about end of September, beginning of October. So.
Okay, great. And the reason I was asking, obviously, in addition to the interest of the questions for the site, but also potentially arranging a site visit for the region or anyone else interested as well. But if I jump into the Q&A, so we've had a question coming from Lee. Has Exeter City Council employed a clerk of works to oversee the project from a quality point of view and to assist the certifier?
They have, yeah. We have a dual role at Gale Snowden. We're appointed by the contractor to collate information, pass it to the Passivhaus Institute, and liaise with the Passivhaus Institute. We're also appointed through an integrated design team, so that's our novated appointment. But on the client side, the client has taken on a technical advisor, a client TA specifically for Passivhaus matters, and he's actually an old colleague. So we don't tend to see much of him, but he does have his input to the client, and he advises the client on quality control.
Great. Our next question is Simeon wanted some clarity on the brackets that you mentioned earlier in the talk. And I believe we had Lee answering it, saying that he potentially suspects it's helping hand brackets for the rain screen facade.
They are, yeah. Typical facade brackets, as you might know, are aluminium, and some of them come with a thermal break, a little pad behind them. That aluminium in 250 mil of insulation bridges 245 millimeters of the insulation and then is isolated for the 5. So that wasn't going to work in our case, and so we looked at a range of different brackets on the market. Some of them actually had plastic inserts, but the ones that you saw on the screen are something called they're a Sistea. I'm trying to remember the name of them. They're a Sistea bracket, but they're stainless steel, which has a much lower thermal conductivity than aluminium.
Okay, great. Oh, that's quite interesting. And did that come up on this site specifically, or has that come up something on previous projects that you guys have worked on?
No, they've specifically come out of this project. So, when we take on a new project, we don't just use items that we've used on previous projects. We always survey, what options are available, what components are available, and what impacts they might have on achieving the environmental factors.
Great. We've got another question in from Lee. What was the AVCL material used in the external walls? Sheet membrane or liquid applied, e.g. passive purple? And then apologies, I could see that the wrap-tight was used. Why was this chosen? So it's a 2-part question, I think.
Okay, there were so yes, you're right. It's wrap-tight. It's a self-adhesive membrane. We had specified a self-adhesive membrane for parts of the building, in particular eaves. And it's not just like a house eaves that's this deep. These eaves are a meter tall once you get down off the insulation past the structure. So there were actually quite large areas that we had to membrane over, despite having airtightness layers of cement particle board, rendered blockwork, in situ concrete. So it was already on the building, and Kia were looking at ways to reduce the risk of airtightness failure and to make parts of the building more robust in terms of being able to complete works without testing, knowing that it had been properly quality checked on site, and then to progress and cover up. And the inclusion of wrap-tight it was actually led by the contractor as a risk reduction measure.
Oh, that's interesting.
So they literally took the wrap-tight and they said, okay, all those areas of SFS with cement particle board, we're just going to apply it to those. And actually, the specified tape that's supposed to go on the Versa panel, so the cement particle board is a A2 Versa panel. The tape that's specified with that system is a strip of wrap-tight, remarkably. So yeah, it just made sense when they said, what do you think about putting wrap-tight over the building? Yeah, fine, great.
Interesting. We've got another question. Did you take account of the insulation anchors to the rain screen facade and the doubling up due to the presence of a breather membrane? Breather membranes installed over MW insulation is tricky to do and often results in gaps, tears, etc.
We did, yes. Yeah, we did. The breather membrane was included as part of the Design for Future Climate Change criteria, or not criteria. It's a methodology really, but so this is actually quite a long answer. I'll try and make it quick. unfortunately, when obviously Grenfell happened, and that was really upsetting for the industry. But the impact of that across the facade and some of the components behind it was, it opened up a new design process, and that culminated in a really heavy breather membrane being switched in for the breather membrane that we had.
Mm.
That breather membrane that you see in black on the building, actually, it in turn created some interstitial condensation questions in the wet areas, so particularly around the spa. But one of the other implications was its weight. It's so heavy. And so, yes, absolutely, we had to have extra fixings. And that was checked with the Passivhaus Institute. They have, they have some charts and tables of the chi values that these have, and we specified how many fixings there would be per square meter over certain wall types, and they added that to the PHPP and tested it in terms of the additional energy loss and the heating energy.
We've got a question in from Dale. Were any calculations undertaken to determine and reduce embodied carbon?
I actually don't know. I don't know that the whole carbon side and the carbon modeling side was something that I didn't really get involved in. I mean, like I say, my role is very much for designing the fabric and the envelope of the building. But I believe some analysis was made either by the Passivhaus Institute or the client team pre-tender, in order to kind of translate and transmute the energy requirements by the Passivhaus Institute across to carbon.
Great. A question in on contracts, I guess. If done again, would you prefer a traditional contract rather than a DMB?
No, I don't think so. The reason for that is whether you have a traditional or design and build contract, you are still going to come up against supply chain issues, design changes. There are still going to be the same issues raised and presented throughout the 5, 6, 7 year period that this project's taken. And for that, you really want the contractor to be fully engaged with the design and to have so at least for the main contractor to at least be able to apportion design responsibility either off down the supply chain to their subcontractors or to try and wedge it over onto the design team.
Right, okay. And they've got a question in from Lauren. How do you manage the air tightness layer being on the back of a plasterboard and stopping the occupiers penetrating that line? It's been great to see it progress when someone that's local.
You don't actually. We haven't had an air tightness layer on the back of the plasterboard, like directly on the back of the plasterboard. The air tightness layer is actually the cement particle board, so it's in the cavity. It's away from the inside face of the wall. It's a risk, but that needs, obviously the residual risk needs to be communicated across to the facilities managers, and to make sure that the operations of the building can recognize what's behind there. And one of the exercises that we've been doing just this last week actually is going back over some of those GAs, those air tightness strategy plans and sections, to make sure that they're updated, not as built, but at least to identify the air tightness components that have actually been installed, where they are, what a maintenance company might expect to see at the junctions, so that at least they know before they go in there what they're going to be working with.
Great. We've got a question from Simeon. How is the building heated overall? Does that make a difference to how you go about the envelope design?
Well, you're getting a bit out of my field there. Um, the, I, I guess that on a project like this, each designer is such a small cog in such a big machine. I I think generally it's heated and cooled through air handling units. Um, the pump gear and the heating gear for the pool water down in the basement is I think is heated by gas. But yeah, actually, to be honest, I don't know the full and proper answer for that.
That's fine. A question in from Andrew. How was the profile distance difference in glazed screening and rain screening resolved?
The profile difference, what in terms of where the glazing sits in relation to the cladding?
Yes, I believe so. Yeah, maybe it's alignment in regard to the envelope for I'm guessing U value perspective, I guess. So
Okay. I mean, the cladding sits, the cladding itself isn't actually part of the U-value calc at all. It does help to reduce um, the uh, the exposure of the outside of the insulation or the outside of the breather membrane to um, to the passage of heat and to infiltration, but it's very much just a decorative surface on the outside, so its position very much is just an aesthetic thing.
mhm.
Of course, if we have it too far off the envelope, then the facade brackets are much longer. Then there's a cost associated with stainless steel facade brackets. So there's a cost element there too to where you have
Yeah.
that facade.
Is a question in from Lee? How far over budget is the project, and who pays? Additionally to that, I guess with this being an exemplar project, I presume there has to be relative flexibility from the client side, the design team side, and also the contractors. And I presume, obviously, there is an element of people needing to be remunerated for their services, because obviously they can't be doing it indefinitely. So it'd be interesting to just hear a general answer, even if you don't know the exact details.
I don't know any of the details, to be honest. I'm not privy to what the current value is or where the costs are at the moment. But I think as designers or as technologists, we have a different perspective to all the budgeting and the cost control. Um, there is an appreciation of obviously how much different components cost that we're specifying. But one thing that we tend not to appreciate is the increase in the cost just due to inflation. If a project is priced in year one and then in year seven it's nearing completion when actually the program was 5 years long on the project side, not the build side, and that could be due to a number of issues like losing contractors during tender, value engineering, all of these aspects to a project that might not be foreseen. Then that inflation starts to take hold and the costs start to increase.
Great. I have a final question as well. Uh, I just wanted to sort of get your gauge from your perspective and Gale Snowden's perspective about what sort of the biggest, I don't know, 5 learnings or 10 learnings that you feel like you've gained whilst working on this project specifically. It'd be quite interesting to hear, obviously, with the depth of experience that the company has in working in low environmental impact sort of buildings of residential and commercial sort of nature, but this obviously being extremely sort of out of the norm.
Yeah, it's. I mean, we. Okay, so five items. Firstly, obviously, airtightness is serious on this scale. You so it all comes down to the air testing strategy, and being able to design a building that is easy to not just construct in terms of air tightness layers, but also to test is really key. And that's been a joint learning outcome for, across the whole project team. Basically, curvy buildings are not easy. Boxy buildings are. Another one I think would be being able to understand and explore every single technology as you are putting together the initial technical design. And that's something that we, as designers, I think we kind of, we try to be economic with the time that we put in at that stage, because we're a little bit concerned about how designs might change, or the project might go away, or it might not be built. But it's really key to make sure that you explore the design in the fullest, even if you're not preparing all of the technical documentation. If you're not doing a detail for the tender pack, at least work it out in your head or with a pencil. I think probably another take-home point is probably not that unique. I know we've got special filtration water. We've got high U values. It's okay. It's a world first, but actually, it's just a really high quality leisure centre. That's all it is. And any practice can do this. And we are at Gale Snowden, we're collaborating with other practices, and we're willing to work with other practices, and we've started to do that in order to bring home leisure centres in other areas, Passivhaus schools, large commercial blocks of flats, and not just a passive house, also using that methodology to achieve net zero carbon.
Great. So I think that brings the talk to a close. Thank you very much, Giles, for that. That is extremely insightful. Thank you, everyone, for attending. Thank you for obviously St. Sidwell's point in a lot of detail. Hopefully, at some point in the near future, we'll be able to go on a tour around, which we can advertise as well. I'm presuming that. Otherwise, we'll have to go when it's just open, I guess, for a swim. Obviously, everyone can see the talks that are coming up. They'll obviously be advertised on the Eventbrite page and shared on social media, etc. So please do come along to the other talks that we have coming up. If you do have any suggestions for other talks in the near future, then please do let us know. We're ears open, always interested in having new collaborations. And there have been a few questions. I will ask Giles after the talk whether he's happy to share the presentation that he's created. Otherwise, the talk will be added to the SIAT YouTube channel, so you should be able to share the actual talk widely as you'd like. So please do, if you need to refer back to it, it should be on there shortly, or also obviously for anyone that wasn't able to join today. So thank you to everyone. Thank you, Giles. Thank you, Joe, for supporting in the background, and also thanks again. So that's us from SIAT Wessex. We'll hope to see you all again soon at one of our future events.
Yes, I just seen all the thank you messages come in. Thank you so much to everyone for coming and joining us. Yeah, it's just been a real pleasure being able to present the project to the SIAT crew, actually, for the first time. So yeah, thanks all for coming.
Thank you. I'm going to stop recording now.